Hello. So in this video we are going to be proving this theorem up here. So we're supposing f from some closed interval a b to r is a bounded function, and we're going to fix some c in between a and b, and we basically want to say that we can split the Riemann integral if it exists at c. So in other words, f is Riemann integrable on a to b, the full section, if and only if it's also Riemann integrable on a to c and c to b, right? So if it's integrable, I can break it up, and if I can break it up and show those pieces are integrable, then the whole thing is integrable, right? It works both directions. Also, I make a note here that the forward part of the proof is one of the suggested problems that we have. So I'm not going to cover that one yet, but if there are questions or whatever, obviously feel free to email, right, or bring it up in office hours, that kind of thing. So I'm going to be doing the reverse implication, meaning that I'm assuming both of these pieces, right, that it's Riemann integrable on a to c and c to b. I want to show that the whole thing is Riemann integrable. Okay, so suppose exactly that. So suppose f is in the Riemann integrable set, right? Is Riemann integrable from a to c, and f is Riemann integrable from c to b. So what does that mean? Well, that means for any epsilon I want, I can find some partition where the upper and lower difference is with an epsilon, right? But I don't want to just say epsilon yet, because my goal is to show that the overall thing is Riemann integrable, which again is an epsilon. So I'm going to let epsilon greater than 0 be given. And now I'm going to use this. So I'm going to note, or since f is, so I'll say since f is Riemann integrable from a to c, there is a partition P1, which again is this x0, x1 up to xn, so that the upper sum for P1 with f minus the lower sum for P1 with f is less than, now I can pick anything I want, right? I could pick 1, delta, 57, whatever. I'm going to pick, for reasons that will become obvious, the epsilon we started with over 2. Right, so remember, I can't change epsilon because that's been set already. Similarly, there is a P2, which is, let's call it W0, W1, Wm. I don't know that they have the same number of elements, although I could force it, but I'm not going to. Such that, and now I'm going to have U P2 of f minus L P2 of f less than epsilon over 2. And it's maybe not obvious with the way I've written this, so let me make it sort of very clear. This x0 is the start here, AC, or A, and then the xn is C. But down here, the P2 I'm choosing, this is going to be for the second piece. So the leftmost part is C, and the rightmost part is B, right? So I'm going to form, I guess, let, define, whatever you want to say, P, a partition. And it's going to be, man, my brackets are really getting bad here. It's going to be, you know what, let me do it this way. See if this even erases well. Yeah, not bad. All right, so P is going to be P1 union P2. But I want to make it clear that this is not just the union of two sets, but it's sort of a nice union of two sets, because I'm going to get P1, which remember is this x naught to xn, but that is this a to c, all of which are to the left of the c to b, right? So all of these points come before all of those points. In particular, I have that it is x0, x1, up to xn. And now xn is c, and so is w naught. So xn is sort of shorthand notation, but I'm just going to make it clear this is w naught, right? So I would choose one or the other. I'll end up choosing xn and getting rid of w naught for whatever reason, but I'm emphasizing that this part, I get all of this, and then it immediately transitions to that. So there's no sort of interlacing happening. That's the key idea here. So this is W1, W2, up to Wm. And in particular, this P, and I'll even write it here, is a partition of A to B, because I have Wm, which is B, I have x naught, which is A, and all of these things are in order, right? x0 is less than x1 is less than x2 up to xn. These things are equal, so I choose one. Which one I choose doesn't make any difference, just fix one of them. And then that one, say xn is less than w1 is less than w2 is less than up to wm. So I have satisfied all my partition requirements. That's the key thing here. Okay. So now I have a partition, so the obvious thing to do is to try out and see if I get my u minus L, right? So I'm going to try this u of the full partition, P on F, minus L full partition, P of F. But remember what the u and l's are. They're just sums across each interval, right? They're the rectangles where the intervals are one to the next, right? The x0 to x1, x1 to x2, etc. And then say xn to w1, w1 to w2, etc. So in particular, if I were to duplicate this, it wouldn't matter, right? Because they're the same point. I'd still be taking the rectangle to the left, rectangle to the right. Even if I had it in the same set, which I'm not going to, it wouldn't matter because I'd be taking a rectangle of width 0, which wouldn't add any area, right? So it wouldn't do any harm. It would just be really silly to do. So what I want to emphasize or point out here is that I can actually write that this is straight up equal, not even like less than or equal or anything. It's actually honestly equal to the P1 of F plus U P2 of F, because I can split this back into the two pieces, right? And that's what U becomes. And then I can do the same thing with L. So keep track of where the minus sign is, right? So I'm going to have minus, and then I'm going to split this as L on P1 plus P2. So this is L P1 on F plus L P2 on F. And it's plus because I'm distributing the negative after, right? I'm saying all other things equal, like if I were to cover up all of this part and look at just the L part, the L itself is equal to L, the L on P is equal to L on P1 plus L on P2. Then the subtraction comes in. But distributing the negative and sort of rearranging this, I can write this as U on P1 comma F, right, this piece minus that piece, L on P1 on F, plus, and then this piece, U P2 on F minus L on P2 on F. But again, sort of unsurprisingly, this is exactly what we had over here, right? So this piece, now I have less than, right? I'm going to replace this thing with the epsilon over 2. So this piece is less than epsilon over 2. This piece also less than epsilon over 2, which means that that sum obviously equal to epsilon. So I have that my u on p minus L on p, which covers all of AB, is equal less than, so it's less than epsilon. Thus, since I've shown that there is a partition where u minus L is less than epsilon for some given epsilon, I have that f is in Riemann integrable set from A to B. Okay, and as mentioned, right, so that's the reverse direction. The forward direction is a suggested problem. So if I have both of those, I have my if and only if, and I am done.